Here are some references that I forgot to mention the last time. The Keeling and Rouhani is a nice book which has some sample programs that are available on the website in C, C++, MATLAB, etc. The Diekman, Hesteby, Anderson, May, all of these are fairly classic and well-known references. Some of the pictures here I got from a web page of Chris Myers at Cornell. That web page may or may not be up anymore. There is a nice review which is more targeted at applied mathematicians in SIAM by Heathcote. And there is a chapter by Boyle and collaborators in Vaccinology Principles and Practice, which deals a little more with how you model vaccines in a population. So I want to go back and revise some terminology that arises in observational epidemiology so that we can use these terms without fear when we encounter them later. So first of all, a population is a collection of individuals with some particular characteristic in common, and it may be as simple a characteristic as all of them belonging to a particular location, a particular district, a particular city, a particular state or country. What determines how diseases occur and spread in the population is governed by a number of different determinants. In some cases, it may be possible to control these determinants and thereby affect the course of the disease. That's what we would like to understand. What are these determinants that affect the population, and how could one potentially control them? So there are three broad types of studies in observational epidemiology. One is called prospective, the second is retrospective, and the third is cross-sectional. So prospective studies, you look forward over a period of time, and you look at association between determinants, between possible determinants in some cases, and the frequency at which the disease occurs in that population. Retrospective, as the term implies, is backward in time, where you compare the frequency of the occurrence of a determinant in groups of diseased and non-diseased individuals. So what was it in the past of those individuals that belonged either to the disease category or the non-disease category that might have been potential determinants that led to disease at this particular point. And here is a sort of cartoon picture of this, where you look at a prospective study. Here you have an obese and lean individuals who are obese or lean at some particular time t. You look at them forward in time, so you compare the incidence over time. And for example, the people over which crosses are there might have people who died at the end of the study. So what you would like here is to understand, is there any relationship between whether a person is obese and lean, and between the possibility between that and whether they die at the end of the study, or they have died, or some reasonable fraction of them that is sufficient to distinguish between these populations have died at the end of the study. So you follow up at intervals to get accurate outcome data all the way across this. On the other hand, the retrospective study, for example, here the example is tire manufacturing workers versus desk employees. So this is what we know now, this is the current understanding of them. What we would like to know is what is the nature of exposure of these employees at some previous time that led to certain mortality at some later time, or the occurrence of a disease at a later time. Cross-sectional studies are at one time, and what they attempt to do is to look at estimates of disease prevalence between various populations and subsets of populations at a particular time. So you have forward in time, backward in time, and at a particular time. These are the three ways of understanding these studies. So the word cohort is used very often. A cohort is just a defined population that consists of individuals that are selected for the purposes of studying the disease and the evolution of a disease. And what one can do is to try and introduce a determinant into one cohort and not have it in the other cohort, or control in some way for the presence of a determinant, look at these cohorts over a period of time, and ask about the frequency at which a disease occurs. So these cohorts can be fairly large. The Taiwan cohort has more than 600,000 participants. The MD Anderson cohort for Mexican American cohort has about 24,000. So these are typical numbers. Some number between 10,000 and a few hundreds of thousands is not unusual in this field. So here are prospective cohort studies and retrospective cohort studies. Again, as an example, if you look at this at 2013, where you have a defined population that is exposed and not exposed, and then you can track them in time and ask at 2033, which fractions of these of the exposed population develops a disease versus does not develop a disease, and the same question for the not exposed population. For the retrospective cohort, you know who has developed a disease or not developed a disease across this. You have to trace back to their exposure in previous years, in 2003 and in 1993, where they were started off with a well-defined population and asked. So now you can go back in time and ask, did the exposure make a difference to their current state of health? A cross-sectional study, as I said, is different groups compared at one time. So for example, you could have group A of 20-year-olds, 50-year-olds, and 60-year-olds, and you compare disease across these. A longitudinal study looks at the same group at different times. So for example, you could look at group A at age 20, and follow it in time. The same group at age 50, the same group at age 80. So this is a prospective study. You go forward in time, but you look at the same group of individuals as they evolve in time. So this is a longitudinal study. The technical term might be a transverse study or cross-sectional study. Is at one time. This is not at one time, but it looks at the same cohort at different times. Here are some useful pieces of terminology again that you will encounter when you think about diseases and disease modeling. The first is the morbidity rate and the second is the mortality rate. Morbidity is just another term for illness, and it measures the proportion of individuals in a population or the risk of an individual in the population of becoming affected. Mortality is another term for death, and it measures the proportion of individuals which die in a particular population. So here are two important terms that it's useful to get a handle on. So the first is incidence and the second is prevalence. So the incidence is a measure of the disease that allows us to determine a person's probability of being diagnosed with the disease during a given period of time. So it's proportional to, or can be counted as, the number of newly diagnosed cases of a disease. Then you have to normalize it in the right way. So it's normalized using a term called the incidence rate, which is the number of new cases of a disease occurring in a specified population during a specified time period, divided by the average number of individuals in that population during that specific time period. It's not enough to say that there is a certain number of new cases. The question is, how long did you look for those new cases? Over what baseline population were those new cases measured? And if you normalize this with respect to those quantities, the time that you measure and the population over which you have measured this, that's when you get to a number that is more characteristic of the disease rather than your specific measurement. Prevalence rate is the total number of cases of a disease in a specified population at a particular point in time, divided by the total number of individuals in that population at that time. So let's just describe this with some examples. So over here is sort of an example of prevalence of selected autoimmune diseases, lupus, MS, type 1 diabetes, etc., etc. And this refers to the number of cases per 100,000 people. So this is at an instant of time. So you don't need to normalize with respect to any time measurement. And now the question is, if I take a snapshot of the population at a particular time, how many individuals out of 100,000 individuals? You have to normalize it to something. So the conventional normalization is some number like 100,000, because then the prevalence of these diseases, the number of order 100. Okay, so about 1% typically of the population is affected by these autoimmune diseases, and these are the numbers that differ between them. So another example, a more specific example to put in numbers in, is that suppose you have a population of 4,000 cattle at a quarantine camp, and there were 60 cases of rinderpest when the population was examined on June 18th. So the prevalence of rinderpest on that particular day, June 18th, would then be 60 divided by 4,000, which is 0.015 or 1.5%, or 15 cases per 1,000 animals, which is a simpler way of specifying the prevalence. So if you wanted to ask the same question about incidence, you could start by saying, if you had an average population of 4,000 cattle in a quarantine camp, so this can fluctuate over a period of a month. It could come down to 3,950, could go up around. This is just an average number that you have. And you have 600 animals that develop symptoms of rinderpest during June. So these are diagnosed cases of rinderpest during that particular time. So the incidence is defined as 600 cases in that time period divided by 4,000, which is the average population over that time. So it's 150 new cases per 1,000 animals over the period of the month. Okay? So the incidence rate is a way of measuring the risk that a susceptible individual in a population has of contracting a disease during a specified time period, because any one of these cattle could potentially have contracted rinderpest. Here's an aside about the disease itself, which you may not have heard of. It's a disease of cloven-hoofed animals, for example, cattle. It's characterized by high mortality. So there are pictures of rinderpest in large numbers of cattle just dead on the ground. It's the most lethal plague known in cattle in its most virulent form. So this is a disease that doesn't exist anymore. It's been eradicated. So until the late 20th century, rinderpest was endemic in a number of countries, but has now been eradicated globally. So this is now an example of a disease that is no longer with us. A disease that affects animals, but still has been eradicated completely. Okay, so that was the introductory part about that. Again, what I will try and do in these lectures is introduce some amount of terminology that is relevant in the broader case of the study of epidemiology, of disease epidemiology, not just particularly the mathematics of infectious diseases, because these terms will recur even when we discuss just the mathematics of the disease. So let's go back to the SIR model. And again, let me remind you that this describes diseases in a population. If you look at a particular individual, you have pathogens setting in at the time of infection over here, which is marked in this case. The load of the amount of pathogen in your bloodstream going up and then coming down. This sometimes is measured in terms of what is called a viral load when you talk about viruses, which is the number of viral particles in a given volume, for example, of your blood, and per ml, depending upon how you choose to measure it. So this is the point where it starts, it begins to reproduce, rises to a maximum, and then comes down. The correlate of this is how you feel, your experience of the disease, which, for example, there is a period up till here where you have viral particles at a fairly low amount so that you don't begin to feel it. So you've been exposed or you have a latent infection. At this point, you become infectious. You can transfer the disease to other people, and then your immune response kicks in, and then you recover at some point. So the part after here, once your viral load has again decreased to a time where it cannot be detected anymore, is the point where you can be said to have recovered. Your immune response has peaked a little after that and then begins to decline. And at this point, you have recovered. So you are exposed, infectious, recovered, and at this initial point, you were susceptible. In terms of the disease itself, there's an incubation period, and then a period where the disease actually sets in, and then the load comes down. Okay. So you can look at this as a medical status and an infection status. So our argument in the last lecture was that populations are made up of individuals, but just choose to group these individuals into different compartments which are labeled accordingly. For example, here susceptible, infected, and recovered. And it's a number in each compartment which you label as S, I, or R, which you want to try and understand. So that if no new individuals enter or leave the population, S plus I plus R must equal N. And it's often convenient to divide by N if N is large enough to have a number that changes smoothly, for example, the small s, small r, and small n. So we ignore, if n is large enough, you can ignore the difference between n and n minus 1, or n minus 1 and n minus 2, and then these numbers become smooth numbers. You don't have to forget about the fact, you can forget about the fact that s, I, and r are technically integers, and if n is large enough. So compartmental models describe these states, for example, s, I, and r, together with a directed graph which tells you about transitions between one to the other. So each edge of the graph is equipped with some rates. For example, this is just a general graph x, y, and z with arrows along it. There could be rates at which you move from here to here or from here to here. And this is if there's an additional in or outflow from this particular system, then the system is considered to be open, otherwise it's said to be closed. Okay. So we will consider a well-mixed population. So S can become I, can become R, and the number of I's affect the rate at which S becomes I. Solid lines, as I mentioned earlier, are transitions, dotted lines are influences, and here we assume that all members of the population can interact with all other members. So now we come back to what we decided we would study, which is the SIR model, which really is a combination of three coupled first order equations for S in time, I in time, and T in time, with functions on the right hand side that depict how S, I, and R interact with each other. The question is, what is the functional form that these functions f1, f2, and f3 can take? The point is to try and decide these by some reasonable arguments. So the most central argument is, first of all, what is the interaction between infected and susceptible people? As I said, there are a bunch of different models for this. And if you say that beta is the number of adequate contacts of a person per unit time, adequate contact is, since it's per unit time, it must be per day, per hour, per week, per month, etc. An adequate contact is a contact that is sufficient to lead to the transmission of infection. So an adequate contact leads to transmission of infection. Then the average number of contacts with infectors per unit time for any one susceptible is beta times I divided by n, because any one of the infection has the proportion I by n of the population is infected. So from here, beta times n times small I times s is the number of cases per unit time due to the S, capital S equal to S, capital N times small s susceptibles, and this form of incidence is called the standard incidence. I also mentioned the last time that there is a standard mass action law, which is the total number of I times the total number of S times some quantity called eta, with eta standing for the mass action coefficient. And this has no direct epidemiological interpretation, but if you compare it to the formulation that I showed you earlier, the standard incidence formula, it shows that beta is proportional to the total number n. So implicitly there is the assumption that the number of effective contacts must increase as you increase the population. This might seem reasonable that if you have the same density and you put more people inside, that beta should increase. There should be some scaling with respect to the population size, but in practice it turns out that that isn't true. You can actually change the population by a factor of 2 or 3 or 4, the total number, and still have beta not changed by very much, typically because you tend to contact the same set of people or the same subset of people in any social situation. There are a bunch of other types of assumptions for the transmission function. This is mass action, this is frequency dependent transmission, but you can put P's and Q's as pars on the S and the I's. You can have more complicated functions. All of these represent different models for how people might interact with each other in order to transfer infection. And depending upon the situation, one may be a little more accurate than the other, but often it's useful to look for the simplest example, and certainly the simplest model here is the model for frequency dependent transmission, where you have the factor of 1 by n entering times beta times S times n. Okay, the second part of it, so the first part of it was the assumption about how infection is transferred. The second part was how someone recovers or how someone leaves the compartment that they're initially assigned to. So this is the first part that we wrote about. The second part just says that there is an exponential distribution of times over which an infected individual leaves the infected compartment upon recovery, and this is the gain in the recovered compartment. Dr by dt is gamma times I. As I said, the conservation law requires that if you take d by dt of s plus I plus r, that must equal 0 because the total number, that is dn by dt, and the total number does not change, assuming there are no births and deaths, and thus the total number remains constant. Okay. So here is an example, as I pointed out earlier, of how S, I and R behave. So at time t equal to 0, you see the infection with one individual in a population of n minus 1 susceptible individuals. As time proceeds along the x-axis, the time unit is arbitrary. You can choose it by choosing essentially the rate at which you define gamma and beta. You can see the number of infectious, the number of susceptible individuals declines precipitously. The number of infected individuals goes up and then comes down with a longish tail, and the number of recovered individuals, which is initially 0, goes up and then saturates to some value. And this is these shapes and the behavior of these curves is what we would like to try and understand. Because these equations are nonlinear, the presence of S times I is quadratic. You can't solve these exactly, but you can certainly understand them numerically. And there are many qualitative aspects of these equations that you can understand straight away. So as I said, since the simple assumption that you recover across some exponentially distributed time scale just basically says that if the probability that an individual is infected at time t when it entered the class is still infected at time x is just a function of exponential of minus gamma at x. X is a time, gamma is an inverse time because gamma is a rate, and this is an exponential distribution of waiting times in each compartment. The important thing is that it is memoryless because it doesn't depend upon the time t at which you enter the compartment. From whatever time you measure, the distribution of times at which you exit the compartment is the same. It's exponential of minus gamma times s. So this may not be an ideal assumption in the context of a specific disease. In fact, it's not an ideal assumption at all because it gives you a high probability of sort of exiting in the compartment even at time t equal to 0 plus epsilon, given this particular form of the probability. So that is usually replaced by something that says that at very short times after infection, you don't leave that compartment. You may peak somewhere in between, and then at long times you will almost certainly have left the compartment. But these distributions become more complicated, and then it also becomes a question of history. The fact that this distribution, the exponential distribution of times is memoryless, is very important because then you don't have to have complicated integral differential equations that describe what your state was at a previous time affecting your state at the current time. Okay. So in general, you could choose some form p of t that is non-decreasing, with p of 0 equal to 1 and p of infinity equal to 0. The one that I showed you earlier was one particular form that had exactly the structure. Then rate at which you leave the compartment is minus dp by dt, and from here you can calculate the mean waiting time in the compartment as basically the integral of dt times p of t. And from here you can go back and then ask these questions of, with more general distributions p of t, what sort of behavior do you have? And these more complicated distributions lead to models where you have integral or integral differential or functional differential equations, all of which are more complicated to analyze. So it's often preferable to work with a simpler model that is easier to study and easier to analyze even numerically than a more complicated model that in many cases or almost all cases may be more biologically realistic but analytically harder to deal with. Okay. All right, so let's just go back very quickly and discuss again what happens to these equations. Look at the I equation here. So if I pull the I term out, the capital term out, this becomes beta times S minus gamma. And remember that we want to see this system where you have n individuals, n large, with one infected individual, and ask, does that infected individual give rise to disease within the population? As I pointed out the last time, this depends upon the sign of beta minus gamma, because if I assume that S is 1, so in these equations I have scaled out, so all of these equations are for the small s, where S, I and R vary only between 0 and 1 because I have scaled out the population size. So over here, whether I becomes bigger or smaller depends upon the size of beta minus gamma. And if beta by gamma is greater than 1, the infected number grows. And this ratio is important enough that it has its own symbol R0 and its own name called the basic reproductive ratio. So as I said, beta by gamma is important quantity. If beta by gamma is greater than 1, then the infection grows within the population. If it is less than 1, it comes down. So remember that beta is the number of adequate contacts of a person per unit time. They lead to infection. And if gamma is the recovery rate, then 1 by gamma is the time that you spend in the infectious compartment. So now you have number of contacts per unit time. If you multiply that by the time, you get total number of contacts that you have during the time that you are infected. So that's a particularly simple interpretation of beta over gamma. So over here, again, as a function of the reproductive ratio, here is the fraction of infected, which, and you can see that there is no epidemic here. There is no finite fraction of the population that is infected at late times. Whereas the moment the reproductive ratio beta over gamma crosses 1, you have a finite number of infected individuals in the population at the maximum. Remember, the infected numbers go up and then they come down again. The question is, what is the value at the maximum? And if you have R0, which is just a little larger than 1, then that maximum value is not very large. The larger the R0 is, the more and more people are infected at the peak of the infection. As I said here, the R0 has a simple interpretation. It's just the number of people that one sick person will infect on average. So hepatitis C is 2 people, Ebola is 2, HIV is 4, SARS is 4, and measles stays right on the right hand side. It's extremely contagious at 18. So typically one person with measles in a population that is susceptible to that particular measles infection will infect 18 more people. So you can see that one person infects 18, each of those 18 will infect 18 other. So this is an infection that rises extremely rapidly, which is why measles is considered to be highly contagious. Okay, so here is some details again about terminology. When we discuss R0, we assume implicitly that the infected outsider is in the host population for the whole period and mixes completely with every individual there, just as the population native would mix. So there are some changes to this. For example, if someone falls ill, their mixing patterns change because if they stay at home and don't go out anymore, they contact far fewer individuals. The other case. So again, here is an example of where a more detailed and more precise model would have a different set of assumptions for infected people and their contact patterns. The second definition is that of a contact number, which is the average number of adequate contacts of a typical infective during the infectious period. So at the point at which the individual becomes infected, the contact number is large, but as time goes on, that person may contact fewer and fewer people. And finally, the replacement number, or sometimes the reproduction number R, is the average number of secondary infections produced by a typical infective during the entire period of infectiousness. All these numbers are equal at the beginning. If you have one infected individual for one particular disease in a susceptible population, then R0, sigma and R are all equal. But where they differ is what happens at later times. As the person's contact changes in time after they fall ill, sigma changes. R, as a consequence of that, R also changes, because R is the total number of individuals that person will contact during the period of infection. Essentially, the R0 assumes that you contact everybody at an equal rate, but these are a little more sensible ways of thinking about the fact that once more and more people become infected, then the chance of your, as an infected individual, of passing on your infection to someone who is susceptible goes down, just because there are fewer susceptible people around to infect. So that's why you have this hierarchy between R0, sigma and R in terms of their definitions. And when you talk about a disease that is already set into the population, R is the more sensible way of talking about it rather than R0. Okay, again, so this is a generic picture that I showed you. What are the initial conditions on this model? So typically what you will have is S0 is S at time t equal to 0 is some S0 greater than 0. You have I at 0 is I0 which is greater than 0, and R of 0, there are no one recovered yet because no one has fallen ill yet. That number is equal to 0. So from here you can take these equations and divide the S equation by the I equation to get di by ds is di by dt divided by ds by dt. And here you will get some number which is minus 1 plus gamma by beta times S. This you can integrate because now this then gives you a relationship between I and S in terms of I0 and S0. So the relationship here is I is I0 plus S0 plus 1 by R0 times the log of S. So this tells you that given a starting point I0 and S0, this is how I and S behave. This is the trajectory of I and S. at some later point. So this is what you will get when you solve that particular equation. So over here you have this number, as if suppose you started off at this particular point, you would wind up at this point. If you started here, you would wind up at this point here. This is susceptible fraction on the x-axis and infective fraction on the y-axis. And as I said, both these x and y's are limited between 0 and 1, and there is an overall limit, the fact that they must all be below this triangle, below that leg of the triangle, which just comes from the constraint of s plus I plus r must be equal to 1. Let's now get to this question of why should you vaccinate? What does vaccination do in the context of diseases? So let's start again with this equation di by dt is beta times s minus gamma times I. Remember that when we said that the condition that a disease should not propagate is that beta s minus gamma should be less than 0, which really implies that beta s should be less than gamma, or s should be less than 1 by r naught if I take the beta to this side, because r naught is beta divided by gamma. So if I have a small population, a smaller number of susceptible individuals, I can satisfy this particular condition. Let's assume that I can replace the s by s times 1 minus p, where p is a fraction of the population, maybe 10%, 20%, 30%, in which case p is something like 0.2, 0.3, 0.4, which changes s therefore. What this does is to change the effective r naught by the initial r naught times the factor of 1 minus p. And here you can just go through these results and ask what that is. So now when you do this, you have reduced p. At some point you will equal this particular condition for which beta times the s times 1 minus p is less than gamma. That special p value is the value at which if you inoculate or if you remove that fraction of people from the susceptible group, then the disease cannot propagate anymore because r naught is less than 1. Okay. So once you do that, what that means is if you immunize a fraction of the susceptibles, this reduces r naught and defines a particular critical threshold PC, which is 1 minus 1 by r naught, okay, which you can figure out from this particular relationship here. And in fact, you can figure it out right away, because the PC here is a 1 in which r naught of I must equal 1. That becomes 1 by r naught, takes I to the other side and change the sign, that gives you this particular relationship here. The larger the r naught, the larger the PC, because the larger the r naught is, the smaller this is, the 1 minus a small number, a number that is very close to 1. Therefore, the larger the number of people who you need to immunize or vaccinate in order to ensure that the disease does not spread. So this is called herd immunity for a specific reason. Again, you don't have to immunize everyone in the population. It's enough to immunize some fraction of them. And depending upon the value of R0, you know what that particular fraction is, which is why the computation of R0 is such an important part of any disease calculation that you want to apply to public policy. Because finally, once or if and once a vaccine is developed for a particular disease, the question is, do you need to administer it to everyone in that population or just some reasonably large number of people in that population? And apart from questions of who should you target it to within that population, should you target it to young people, older people, the whole somebody chosen random from the population itself, etc. These are higher order questions that for which you need to understand a little more about how the disease is transmitted between different individuals. But here is just what you should take away from this is the idea of herd immunity, that beyond a point, you don't have to vaccinate more. If you have a disease with an R naught equal to 5, then 1 by R naught is 1 by 5, which is 0.2. So if you immunize 80% of your population, that's enough to prevent the disease from spreading. You don't have to immunize 100% of the population. So just a note about when various vaccinations were developed. 1798 is the oldest one, the smallpox vaccine due to Jenner. Cholera, typhoid, BCG came in the 1920s, yellow fever in the 1930s, measles, mumps and rubella, the MMR series came in the 1960s. And rotavirus, which for childhood diarrhea comes from the 1990s and onward, and is still under development. There is no vaccine for the HIV/AIDS yet. There is interest in a lot of development of vaccines for different types of diseases. We don't have one for malaria, for example, but all of these are under development. People think about these, and certainly finding an efficient vaccine, for example, for Ebola, would be a real important contribution to the understanding of how to control the epidemiology of certainly a very important disease. Okay, so now let's do a little more that is mathematical about these, but the advantage with this simple model is that much of this analysis you can actually do in a fairly straightforward manner. So let's ask, what is the fraction of the population affected within the SIR model? So if you go back to taking the S equation and dividing by the R equation, you can get rid of the factor of I. So ds by dt divided by dr by dt is just minus beta by gamma times S, the factor of S, which is minus R0 times S. This you can now integrate, because log S minus log S0 is minus R0 times R, and this you can then write as S equal to S0 exponential of minus R0 times R. So this says that, look, R, so now I am going back to the situation where R is, Si and R are between 0 and n. If I put an n here for the maximum possible value then R can take, then S is always greater than or equal to S0 exponential minus R0 times n. Okay. So if I look at, if I say that S infinity at long time must be anywhere between 0 and n, and R infinity must be n minus S infinity, this gives me a relationship between the S infinity, the S0, the R0 and the n that sits there. Okay. And this you cannot do analytically, but you can certainly do it graphically. Find out what is the number of susceptible people left in the population at long times, how does that relate to the R0 of the population and the S0, the initial value of the susceptibility. By plotting these functions as I have done here, you can then relate one to the other, okay, and find out how many other people at the end of the epidemic as a function of R0, how many people have not contracted the disease, and this is the relationship that tells you about that. If you go back to that equation for R, dr by dt is gamma times I, which is gamma times n minus n, S minus R, and over here you put in the value for S here, which S is S0 exponential minus R times R0. This is a somewhat complicated equation because you have the exponential term in R here and a dr by dt here, along with other terms, all of which also depend upon time. But if the epidemic is not large, you can expand the exponential. So you can write S0 exponential minus R by R0 as S0 times 1 minus R by R0 plus higher order terms. So you do that in this particular step and then write the equation including the next order term here, which is R0 squared divided by 2. This is just a Taylor expansion, assuming that R times R0 is small. Once that is done, you get dr by dt is, you've eliminated these terms here, so it's approximately equal to this value here. Collect the terms one by one, and this equation you can solve as it turns out. So R of t is this complicated function, a tan hyperbolic of an alpha function times with a phase factor phi, and alpha and phi can also be calculated depending upon the values of S0, n and R0. So this is doable, it's actually writable in closed form, even though the original equation here couldn't have been solved exactly. The second equation with the approximation that you just keep the first few terms when you expand, that can be solved. And finally you get an equation for dr by dt in terms of this alpha quantity that I just described. In the Bombay plague epidemic, to which Kermack and McKendrick fitted their data, the assumption was that since most of the infected died, you could fit the death rate dr by dt. So instead of saying removed, these were people who actually died because they died as they left the infected compartment. You could fit this to the R of t expression, and given the population size, it was not a severe epidemic, so all of the approximations that were made could actually go through. And this is as the fit of that particular function to the plague incidence, and was as a function of time in weeks. So as I said, this is one of the most reproduced figures in books on mathematical epidemiology, and this is where the calculation that leads to that particular graph comes from. And it's a very clever idea. It's a sort of it's a nice bit of applied mathematics from 100 years old that actually takes a set of nonlinear equations like this and winds up with something that you can actually compare in a realistic manner with data. This is the original application of the SIR model. Okay, so we have so far been doing a very simple calculation. We assume that nobody entered or exited the population, so that the total number of S, I and R remain the same. The R equation doesn't really affect it doesn't turn up in any other equation. So anything that leaves the I population, whether you say they recovered, whether you say they did, it doesn't really matter, which is why this particular approximation worked well for the plague epidemic. If you just said that removal is equivalent to death, the removal rate is equivalent to the death rate, and therefore I can use what I have calculated for the death rate and fit it to what is I know from the experimental data. But now you can add additional terms here, and that is to assume that births and deaths also occur, and this is a term that says S increases by a factor of mu. There are new births at every time. S is the number per unit time. It's a rate. So this is the rate over here. rate mu. And this is the death term that says that I remove individuals from the population at some rate r. Okay. So once you recover, even recovered individuals are removed from the population. So these die, and you assume that there is no mortality. I mean, there is a mortality term that comes from here. The mu I is also reduced. So you can die here, you can die here, you can add the population here, and you can die here. So that's really the structure of this. The death rate and the birth rate are the same. So on average, the number of individuals in the population remains the same. But now the question is, what do these additional terms, what do they mean and what do they imply? So this is called adding demography to the SI. Demography is populations. So this includes the dynamics of the base population itself and allows n to fluctuate and asks what does that do to the basic structure of the SIR equations. If you go back and look at the argument again for what we did to look at di by dt and whether di by dt could grow or not grow, you can see that all that happens is that the beta s, the gamma, etc. are now combined into a term that multiplies I, and R naught then is just beta divided by gamma plus mu. So essentially all that has happened is that beta by gamma has become beta divided by gamma plus mu, with the mu coming in from here. So now you have the same argument that you used the last time. If R naught is less than 1, then the epidemic grows in the population. If R naught is greater than 1, then the epidemic, if R naught is less than 1, the epidemic comes down. If R naught is greater than 1, it propagates within the population. But now the definition of R naught is modified a little bit by the existence of demographics. Okay. What else happens? So if you remember from the SIR equation, the earlier plot, you had the number of susceptible individuals come down and plateau. You had the number of infected individuals go up and then come down to 0. And then you had the number of recovered individuals start off at 0, go up and then plateau to some value here there. So that finally you had some fraction of susceptibles left over. You had some fractions of recovered left over. You had no infected at all at long time. So the total number of susceptible, remaining susceptible and recovered should add up to 1 if you normalize correctly with respect to the population. But what happens in this particular case? So what happens here is that if you can, in order to ask what happens at long time, what are the stable equilibria at long time, you can set the left hand side equal to 0 and then ask, are there values for I, S and R, which are I star, S star and R star, which reflect that stable situation. So if you look at this equation here, it's I times beta S minus gamma minus mu is 0. So I star is 0, or so either this quantity must be 0 or this quantity must be 0. If this quantity is 0, that gives S star is 1 by R naught because it's gamma plus mu divided by beta. So the susceptible value saturates at a value of 1 by R naught. In addition, I can now take this and put it back into these equations here and then ask what is the value of I star and what is the value of R star that appears. Then answers are here. S star, I star, R star is 1 by R naught, which we just calculated, mu by beta times R naught minus 1, 1 minus 1 by R naught minus mu by beta times R naught minus 1. So this is the stable values for S, I and R. So now notice very importantly that at long times, you can have a non-zero fraction of infected individuals within the population. This is called a disease becoming endemic, which means it is constantly present at some low level within the population. So now what is here again within the simple model is that just accounting for demographics, for the birth and death of individuals within this population, you have now saturated, you are now able to stabilize some number of infected which always remain within the population as a stable state. And that fraction is specified in terms of the R naught, the mu, the beta and the other parameters that enter the calculation here. Okay. So you can also see that as mu goes to 0, as there are no births or deaths anymore, this term vanishes, that term vanishes, and you have 1 by R naught for the S, and you have 1 minus 1 by R naught for the R, and no infecteds anymore. So this gives you back the result that you had earlier. So here is the bifurcation diagram for the SIR model. This is the stable disease-free equilibrium for essentially R naught here, less than 1 and for greater than 1. And this is a stable endemic equilibrium for in the presence of births and deaths. So this is the infected fraction here. So at this case, you have for R naught less than 0, you have a stable disease-free equilibrium over here, and unstable disease-free equilibrium on the right-hand side. Okay. Let's talk a little bit about how difficult or easy it is to estimate R naught. So remember that R naught is beta times gamma plus mu, and the di by dt equation is beta minus gamma minus mu times I. I can combine these terms here, pull the beta out to get beta times 1 minus 1 by R naught times I. Okay. So di by dt, once I simplify this further, is gamma plus mu times r naught minus 1 times I, which I can then integrate. This says that I is the initial value of I started out with, I at t equal to 0, times an exponential of this particular term here. Okay. If I have that particular quantity, then I can ask, okay, can I fit this particular relation? So R naught here is S0 times R naught, technically speaking, because that reflects the initial number within that population. And if you try to do this on real data, typically the problem is that you would have a lot of noise, because the point at which you're fitting this data to very short-term behavior, to the behavior of the infected individuals at short initial times. If you do that, this is also the period where you're talking about numbers like 1, 3, 5, 10, 15, so you can have large fluctuations in those numbers. It's these fluctuations, so these are many different runs of assimilation which people get ill and transfer that infection to other people. Along with these many runs, you can see that while on average this is an R naught greater than 0 situation, the number of people infected goes up. There is a lot of variation in each individual curve, and this is the number of infectors as the distribution of the number of infectors as a function of time corresponding to that data here. So often this is hard because just determining this particular quantity involving R naught from here is made very difficult because of the large fluctuations that exist, large stochastic fluctuations that exist at small time. The other problem, of course, is that you don't know what S0 is. So the only thing that this gives you is the combination of S0 times R naught, and often it's difficult to disentangle the relative proportion of S0 and R naught to that particular, the relative contributions of that term to this particular growth. Here are some more things that you can do with the model. The force of infection, as I said, is the S by dt is minus lambda times S, where lambda is beta I divided by n in the standard incidence model. The time spent in the susceptible class is the inverse, the 1 over beta I star. So from here you can calculate I star in terms of these particular quantities, mu over gamma plus mu times 1 minus 1 by R naught, and the mean age of infection here is 1 by mu times R naught minus 1. Okay, and this, if I set the mean age of infection here to this quantity here in terms of a lifespan, R naught minus 1 is approximately the lifespan divided by the mean age of infection. Okay, and yeah, over here is a function of mu and a function of the basic reproductive ratio for 3 different values of mu, which is 1 by mu is 40 years, 1 by mu is 60 years, 1 by mu is 80 years. You can calculate the mean age of infection and then try to fit this with the data to ask what is R naught? What does the R naught actually correspond to? You can also look at disease in different ways. For example, you can look at disease in terms of specific markers that are present in the blood, or disease-specific antigens in the blood. The term used is seropositive if you have antigens to a particular disease present, suggesting that either you are infectious at this particular point of time or you are immune because you have contracted the disease earlier. If you're seronegative, you have no such antigens present, and so you are potentially a naive candidate for acquiring that particular disease. So if you measure the proportion of uninfected individuals in the population, then S is 1 by R naught, except for the fact that usual seropositivity has a definite correlation with age. You cannot assume that the population is completely uniform, because the older you are, the more chances you have of having contracted that infection or closely related infection at some earlier point, and therefore having antibodies that are related to that. So you can use these more complicated age-dependent nature of likelihood of susceptibility, at least in one particular way. You know the mean age of infection in terms of R naught, and then you can determine the probability that the person is still susceptible at age A in terms of this particular expression, and then from here, using seropositivity data, try and fit the value of R naught. It's a complicated situation, because you do need to know as a function of age what is the seropositivity that you associate with the particular individual. There are uncertainties in that particular determination, but once you put that together, you can try and answer this particular question. Let's talk briefly about the approach to equilibrium. As I said, the moment you account for demographics, you have saturation values of I, of R, and S. But how do you get there? So for this, the generic way of doing it is to start with a set of equations that defines the dynamics of your model. So your dynamical system dni by dt is some function of n1, n2, and n3. And the properties of these about the fixed point are determined by the Jacobian, which for a set of 3 variables is where you have f1, f2, and f3 are these particular combinations of terms. So over here, the role of the f's are played by the functions on the right hand side of these equations. The n1, n2 and n3 are the same as the s, I and r, and then you can take this and ask, what do I get if I calculate the Jacobian about these fixed points? So the Jacobian is beta I star minus mu minus beta s star 0, beta I star, etc., etc. And to understand the behavior of the system about those fixed points, what I need to do is to calculate the determinant. So here is that function. The determinant is obtained by subtracting lambda from the diagonal elements and then calculating the determinant, setting it equal to 0, which amounts to finding the solutions of this particular equation here. Again, this is algebra, I'll leave it to you to do. But the eigenvalues of the Jacobian are from these solutions, and there is one negative eigenvalue of minus mu, and there are two other eigenvalues, lambda 2 and lambda 3, which is minus mu times r naught by 2 plus some term there that has an I associated. So this is a set of equations that come, solutions that come in complex conjugate pairs. The existence of these solutions with a complex part suggests that there are oscillations in the system which are damped because of this negative eigenvalue term that appears before this. So these terms can be defined, A can be defined in terms of those quantities there. So over here, you just have to recognize that setting mu going to 0, which is having no demographics at all, sets A to infinity. A to infinity gets rid of this term, and then you have a completely overdamped approach, but no oscillations at all, to the final state of the SIR model. But over here, the moment you have a non-zero mu, then you have the possibility of oscillation that comes from that, and these oscillations can be computed from solutions to that equation. So this is the fraction of the infectious individuals, I. This is time in years, and this is a particular choice of the alpha, beta, and the beta, the gamma, and the mu that enter those equations. And you can see that they are damped out. These are oscillations in the system. These are damped out. So finally they will approach the value of I star that we calculated earlier. But the approach to this value is oscillatory. And the period is connected to the values of beta, gamma, and mu that I showed you earlier. So here is a calculation that looks at infectious period, which is the gamma inverse as a period, transmission rate, which is beta, and this is the period of the oscillation. So as a function of changing this at a particular transmission rate at a certain infectious period, you can have a certain oscillation period. And if you look at relatively small transmission rates here and relatively small, essentially infectious period anywhere here, you can find the period of oscillation actually can be fairly large. If you have periodic behavior in some function about fixed point of periodic, an oscillatory approach to that fixed point, you can ask what happens if I force this. And there are very natural ways of forcing a system like this. For example, just the fact that you have seasons ensures that there is some periodic component that has a period of 1 year in the terms that are included in your equation. For example, beta of t, which is the force which is proportional to the force of infection, could have some time dependent term t, and naively you might believe that frequency would be a year. The time period would be a year, the frequency would be 1 over a year across which. So now you can ask, what does having time dependent forcing in these equations do to the structures of those equations? And the answer is that you can amplify the disease if you are sufficiently close to the natural period of that oscillation. If you force more strongly, you tend to have more depletion of susceptibles and more gradual relaxation back to the initial state. And you can have multiple attractors. You can have attractors that have, for example, have a period of 2 years or a period of 6 years. You may be able to switch between them depending upon what your behavior is. So these were the simplest model. The SIR model is just one compartment of S, one compartment of I, one compartment of R. But there are many ways to make this situation more complex. For example, you could have structured models in which you subdivide compartments in particular ways. For example, in the discussion of sexually transmitted disease, you could have a high risk and a low risk population, and then you would have to define different compartments for each of these. For example, here, because the population evolves very rapidly, an SIS model is fine because you can calculate, you can be infected by the same disease again after a short while because the pathogen has mutated sufficiently within that period that your immune system does not recognize it as something that it has encountered earlier. So over here, the equation that you would write for the high risk population infected and the low risk population infected would have cross terms that provide for infection by a high risk or a low risk individual. And the structure of these particular terms here and the presence of the gamma, which is a removal term from the high risk and the low risk population, also have to be accounted for. Here again, you can linearize about the disease-free population. You get a Jacobian which has this particular structure, and then you can ask about the eigenvalues of that Jacobian and what it does. And typically, it turns out that these will have some exponential behavior. Some exponential increases the number of infectious and remember, you're doing all of this about the disease-free population. You want to start out here, and then at long time, essentially the largest eigenvalue that governs both of these behaviors. So you will see that both of these will tend to grow at the same scale, a straight line on a log-log plot, which is slave to the value of R0. And then they will saturate to different values of the infected individuals between low risk and high risk. But for that, you have to solve the full set of equations. The Jacobian will merely tell you about the stability about the disease-free fixed point. You can also do age structuring. You can make each compartment more complicated by accounting for the fact that there are children, teenagers, adults, etc., etc. Typically, for diseases that are measles, childhood diseases, you have a high-risk class of children and a low-risk class of adults. So here, age, in principle, the age changes continuously between the adult and the child. But here's an example where a compartment model is actually better than doing a more complicated calculation, because the way in which children interact with other children is different from the way they interact with other adults. And therefore, it actually makes sense to consider children as a compartment of their own, where they interact primarily with individuals from the same compartment. So for example, here you could have children and adults here. You could have essentially the dotted line moving from between, that affects the transition between S and I, largely coming from here. You could have some amount of leakage from here to here, some amount of influence of at the adult stage between the infected and the susceptible. But the numbers that you would choose here would really favor children acquiring this infection from other children within the population. You could also look at the case of multiple pathogens, for example, S, I, and R, but you have I1 and I2. I2 would be one pathogen, I1 would be another pathogen. Then you could ask, if you have these two pathogens competing, what happens in the population? Which pathogen wins out? Do they both win out roughly equally? It turns out that if you have cross immunity, that if you are infected by pathogen 2 and that gives you immunity to pathogen 1, then whichever strain grows faster, has a higher R0, will drive the other one to extinction. So evolution itself favors mutants with higher R0, that particular value. And this really comes from higher transmission rates, larger beta, low long-lasting infection, which is large, which is a small value of well, that should not be mu but gamma, but small value of gamma, and low probability of mortality, which means gamma is also very small. So that gives you a large value of R0. And if there is no cross immunity, you can have various complicated coupling through response, which is that if you are ill as a consequence of pathogen 1, that influences your ability to contact other people, therefore suppressing your ability to contract pathogen 2. Okay, so there is some anti-correlation involved in the way you contract diseases, but that seems to be more complicated and requires the fact that you change your beta or the way you contact people, and that has to be accounted for. And one can sort of look out at, if you compare the proportion that are susceptible versus the reproductive ratio and see which strain wins out in different regimes. There are regimes in which both strains win, both strains lose, and one increases at the expense of the other. Okay, so that's all that I had to do today. And the next time we will go a little further from the SIR model, and we will begin to look at models that have, for example, network-like structure. We'll begin to talk a little bit about agents. We may explore some of these particular issues a little bit more. For example, seropositivity. What is the right way to account for seropositivity? What are issues associated with vaccination? But from now, we will do a sort of broader spectrum of topics than we have covered so far. And as before, I will try and put in a little more information about basic epidemiology as we go on, just so that we are on the same page with respect to terminology, and you're not surprised when you encounter these terms anymore. Okay. So I will send you a message about when my next lecture is. I actually don't